I have 3 groups for lab that have been turned into me. As you saw, right after lab, we got the 5 group reservation. So the last 2 groups will be 4 members in the group. So work on getting your groups together. I would like to, by lab time, by the time we're done with the lab tomorrow, to have all of the project topics taken care of, since it was supposed to have been last week. So just to get that timeline in your heads. As a reminder, the topics need to be from this semester, not from last semester. One thing that's not written that is an additional rule is they can't be the topics that were done last year. So you can't just go out and look at a poster and say, yeah, I'm going to reproduce what they did. That's fine. Excuse me? You could do something nuclear, but you can't do a cloud chamber.
What if I get my hands on some uranium?
We've got plenty of uranium rocks. Now, if it's enriched uranium, we're in trouble. But naturally occurring uranium has very, very little of the uranium-235 that they make bombs out of. It has a lot of uranium-238 that they make plutonium out of that they make bombs out of. But it takes work to convert that to plutonium. Okay, moving forward. Today, capacitors, and we're going to learn about resistors and Ohm's law. So let's get to finishing something I started last class period and I just forgot to finish with. And that is when we talked about the electrocardiographs, I should have talked about something we all know. On TV, when somebody, has a heart attack, what do? Yeah. They put the defibrillator on them. Has anybody ever actually put a defibrillator on a person? Yeah. It's not very many usually. I don't think I ever put one on an actual person. I put plenty of dummies. Did CPR on a dead guy, but never actually used the defibrillator. Yeah. Okay, just for reference, at PUC, part of our ambulance range goes out to Lake Berryessa, which takes about an hour to get there. And this guy had been having chest pain all day and finally walked outside to tell his family, I don't feel very good, and he collapsed. And by the time we got there an hour later, he was blue. So you knew you were too late. But I did CPR on him. Okay, so first of all, not every heart attack is shockable. In fact, there are really only 3 rhythms that are shockable. You have ventricular tachycardia. Tachy means fast. So this is usually just written as VTAC, which means that your ventricles are just going really quick. Or ventricular fibrillation. Fibrillation, my EMT teacher described it as quivering. And if you look in the picture here, what you have is current going in loops. So the tissue is contracting, release, contract, release, with just loops, not having any organization to it. And so if you have part of the ventricle contracting, part of it isn't, you're not actually pumping blood. And so as he said, it's quivering and not pumping blood. And so here's what the VFib looks like. The ventricular fibrillation is usually just written as VFib. And then there's another one that I don't even know, supraventricular tachycardia. Other rhythms like AFib, atrial fibrillation, generally not shocked. I was trying to read up on why don't you shock AFib. And atrial fibrillation is where you have basically currents going in circles in the atria. And it suggested when you have AFib, you start developing blood clots in the heart. And then if you shock it and make the heart work right, you're going to push those blood clots into the lungs and cause pulmonary emboli, which I know about. So remember I told you we used to have a defibrillator that gave us a readout, and so we could look at that and say, ooh, shock or no shock. And they we don't want any humans making decisions. We're just going to let the machine do it. And so they swapped them out and put ones where you just put the 2 pads on, and then you press a button, tells you stand back, it analyzes and says, shock indicated. You press a button, you stay standing back, and shocks them. What's the goal of shocking a person? Now, let me be clear. Shocking a person who's either in VTAC or VFib. Not just, I want to make them in pain. Go ahead.
To stop the heart.
The goal is to stop the heart. Not many people know that. I'm impressed. He paid attention in his class. The goal is to stop the heart. How is a big shock going to stop the heart? Go ahead.
Wouldn't it make everything contract?
Yeah. What you're doing, and of course you have to have the voltage going the right direction to make the current go the right direction, to make everything depolarize in the heart. And so basically you're making the whole heart go and stop. Of course, after it's depolarized, what should naturally happen? It should repolarize, and then if you're getting the signal from the sinus, then maybe it'll go right through the atrium, collect at the AV node, go down that bundle of His and up through the Purkinje fibers, and good as new. That's the goal. The goal is basically, it's the same as on a computer. Well, back in the old days, you guys never had this. It used to be you hit Control-Alt-Delete, and instantly the computer rebooted. Now it brings up Task Mangler, and you do whatever. That's what you're doing with the defibrillator. You're trying to stop the heart. Now, when you stop the heart, what things can happen? Okay, I had a few answers that I couldn't make out.
Could it just stay stopped?
It could stay stopped. One of the outcomes, you shock them and hey, now they're in asystole. Asystole means no beat. It's not contracting anymore. Well, that's not compatible with life. And it's also not a shockable rhythm. That was the terminology my ENT teacher used. He also liked to use circling the drain of life. And so you kill them. It's kind of bad, right? One of the reasons you don't want to just willy-nilly have somebody shock somebody if they're not in a shockable rhythm. Because if you stop the heart and they're not in one of the rhythms that's likely to convert to working correctly, you had a chance of killing them and no chance of saving them. That's not a good odds move. So one option is you could kill them. Another option is it could return to the same rhythm. Well, it didn't do much of anything. Another option is it could convert to a different rhythm. Hopefully a good rhythm, maybe a shockable rhythm. And so you're kind of playing with some odds. What about CPR? What good does CPR do?
Keeps blood flowing through your body.
Keeps what?
Blood flowing through your body.
Okay, it keeps blood flowing through the body, and oxygenated blood no less. Back when I was an EMT, we were supposed to breathe like, if you're by yourself, you do 15 two breaths. Now you don't even do that, right? You just pump away because they figure the compressions on the chest is going to cause air to move in and out of the lungs enough to keep it oxygenated. So you're moving blood through the body so that organs don't die. And hopefully you get to a hospital and somebody can do something to help them. What are your odds of survival once CPR is started? If you're not in a hospital, it's 2 to 3%. What are the odds of survival if CPR isn't started? 2 to 3%. It really doesn't increase your odds of survival very much. That's what I learned. I also was very curious about reading about old forms of CPR. My favorite one? Well, one was to roll them over a log. That was kind of fun. But my favorite one was to get out your tobacco and blow smoke up their tailpipe. I think that's the correct way of saying it. That used to be an approved method of CPR. Yes. I probably would not have been an EMT in that era. Anyway, that's not really physics, but this physics about stopping the heart, that's good understanding. Now, just a few more things. When you put this electricity through the body and through the heart, is it good for you? Generally speaking, no. Because you're putting a lot of energy through things, and so you're probably going to burn some tissue. And in fact, despite what you see on television, you never, ever, ever, ever shock somebody through clothing because you don't want to catch on fire. Or things like, I know this gets personal, but if a woman has an underwire brassiere and you leave that on, that's really bad. So, what? Okay. You want to cause the least amount of damage possible. So at least the protocols when I was at EMT was you start at the lowest energy setting for your defibrillator. Usually they have 3 settings. You start at the lowest one, you shock them, and if it doesn't convert, then you raise it to the middle setting and you shock them again. If it doesn't convert, raise it to the high setting, shock them again. And if it doesn't convert, you do CPR for I forgot how long it was, like a minute, and then you just stay at the highest energy and do another set of 3. If it doesn't convert, do CPR for another minute and do one last set of 3. And if it doesn't convert, then she's dead, Jim. That was our protocol. Okay. Moving on then. Capacitors. We have introduced the capacitor but not talked about it specifically. So what is a capacitor? It is a device to store energy in an electric field. That's one way of describing it. Another way is to store a charge separation. Now that word separation is important. You're not storing charge with the capacitor, you're storing a charge separation. So you're putting positive charge on one side, negative charge on the other. So this picture here on the right shows a parallel plate capacitor on top. 2 parallel plates. You connect it to a battery, and that battery, because it has a positive pole, that positive pole means that it has more positive charge. Negative pole is more negative. I actually think I took the slide out on how battery works. And so the positive side is going to attract electrons. So you're going to have electrons that leaving that side A, let me zoom in a little, leaving that side A positive because electrons were pulled away. Well, the negative side has excess electrons, so it pushes electrons up to the negative side, and so side B gets the negative charge. Now a battery, just like the capacitor, it doesn't create charge, it doesn't destroy charge, it doesn't store charge. All it does is it gives charge energy. And by giving the charge energy, you create the separation of charge. So the battery is just giving charge energy. It has the energy to move the charge. Now, if you think about this, if we start with 2 parallel plates and each one is neutral, how much work is required to move an electron from one plate to the other? How much work is required to go from 0 volts to 0 volts? 0, right? No change in energy. But as soon as you move that charge across, now we're going to have a voltage difference between the 2 plates because one is now positive and one is negative. That's going to create an electric field and a voltage difference. So to move the second electron is going to require a little bit of work. But when you move the second electron, you've doubled the electric field. It's going to take more work to move the third one and so on. So to move that charge is going to take more and more energy. And so we're going to look very soon, like 3 slides, at the equation for energy, but you can see it's going to take energy to move the charge across, and eventually you'll get to the point where the voltage difference between the 2 plates is the same as the voltage difference of the battery, and then you don't move any more charge. So this is the parallel plate capacitor, very easy to work with. Capacitance, this is, I think, the next slide. Capacitance is defined as the ratio of charge separation to voltage difference. So if I have a large capacitor, well, I usually like to solve this for Q. So if we solve this for Q, it's like some home shopping network QVC. And so if I have a large capacitor and I connect it to a 1.2 volt cell, the amount of charge that's moved is large because it's a large capacitance. If it's a small capacitor, the amount of charge that will be moved is small. So the capacitance tells me about how much charge I can store, the separation on this device. Now this is another version of a capacitor. What's different about this capacitor? Okay, it's rolled up. And when it's rolled up, if you look at this one that's marked negative here, I'll mark the negative one in blue. The orange is an insulator to make sure that you don't have direct contact so charge can flow from one plate to another. And on both sides of that, it has the positive. Now, we learned that charge is stored in the outside of conductors. And in the parallel plate capacitor, in this situation here, you would have all of the negative on this side, all of the positive on this side, and the outsides would have been neutral. But in this situation, you're going to have the opposite charge on both sides. So you're going to store charge on both sides of the plate instead of one side. So you're doubling the surface area by having it rolled up. And by rolling it up, you can generally get things closer together. And we'll learn that these are important for the capacitance value. So these give you a higher capacitance. And if you want the little solid state capacitors, things like these here, actually this one here is probably also, those things are made imagine that I didn't touch something like this using geometry to get a very close packing between the two plates. So those are probably your highest efficiency in terms of size compared to capacitance. So the goal of capacitor, to store energy in the form of an electric field. In my picture here, once I have it charged, what kind of electric field am I going to have? Pointing which direction? Away from positive toward negative. That's right. So it's going to create this electric field, and that's what's going to store the energy. Now, one thing I've kind of glossed over up to now, the electric field goes like that. We can use Gauss's law to calculate the electric field, provided that we are far from the edges. If we're far from the edges, that is, if the separation between these two that we'll call D is small compared to the distance we are from the edge, then locally it looks like you have an infinite plane. That is, like the area goes on forever. And in that case, we can use Gauss's law to find the relationship between the electric field and the charge density pretty simply. Given the time, I don't think I should go over it. I definitely will in class tomorrow if you want to come for the Physics 252 class tomorrow. There won't be actually much calculus at all. It'll mostly be how to solve things with Gauss's law. But we can find it not very difficult using Gauss's law. The voltage difference, we've already seen this equation, so this is just repeated. And if we combine those two relationships, that is, if I say delta V is equal to Q over C. There's actually a step missing. The electric field, this is actually, I should have realized, this is the result you get from using Gauss's law for how strong the electric field is given the charge density, the Q over A. So the electric field between the parallel plate capacitor is proportional to the charge separation and inversely proportional to the area. The capacitance and the voltage relate such that I could put capacitance is equal to Q over ED. That is, I substitute for delta V, electric field times the separation. And then if I substitute for electric field in here, That's going to be Q over notice the Q's are going to cancel, and it's the area times epsilon over the separation. So for a parallel plate capacitor, the capacitance can be determined just from the physical parameters, which should be right here. Well, it's actually going back one slide. This equation here for the electric field is assuming that it's air between the plates. If you put something besides air between the plates, then you have something that we call a dielectric. Dielectrics, things that have a dipole moment. So something that has a dipole moment might be, paper has a certain dipole moment. And so you put paper in there, and if you put something with a dipole moment between a positive and negative plate, each of the electric dipoles is going to rotate so that the positive side of your electric dipole is attracted to the negative plate. But when you do that, then you have a whole bunch of electric dipoles that are aligned in the opposite direction from the plates. Notice that the positive side was here on the plate, and the positive side is away on the dipoles, which gives you a net effect of having in the middle of your capacitor something that's reversed with the charge, giving you electric field in the opposite direction. Well, when you add electric fields, you add them as vectors. And so I have electric field like this plus electric field like this. What's that going to do to the total electric field? It's going to decrease it. And by decreasing that total electric field, you raise how much charge you can actually store on this thing. And so that's why this K, called the dielectric constant, is a number that tells you how strong the dipoles are. And actually, that's not a K. Who knows what that really is? Nobody, apparently. That's a Greek letter, kappa. It's capital kappa. I think it's capital. Anyway, so the dielectric constant tells you how polarizable it is. And so if you put a dielectric in there, the capacitance increases proportional to that dielectric constant. So if I remembered right, yes, here is the dielectric constants for some common materials. So you notice vacuum has dielectric constant of exactly 1. Air is very close to 1, 1.00054. Right, so that's a reasonably the same as vacuum. The right column shows you the dielectric strength in kilovolts per millimeter. We had a group that looked this up for the first lab. What group was that? Who measured the voltage that you could get from the Van de Graaff generator?
Oh my God, was it?
Yeah. And what you looked at was the dielectric strength of air. Dielectric strength of air, about 3 kilovolts, 3,000 volts per millimeter, or 30,000 volts per centimeter, because you measure in centimeters, right? And so then they measured the length of an arc, and they were able to get the voltage, because the dielectric strength is the volts per distance, otherwise known as electric field, the maximum electric field that you can have in that medium before you actually have electricity pass through it before it starts conducting. And so for air, somewhere around 30,000 volts per centimeter is where it starts conducting, where you have arcs go through the air. If you have something with a low dielectric strength, you can't go to very large voltages in your capacitor before it starts arcing. A high dielectric strength, you can put higher voltages before it starts arcing. So if you look at capacitors, their ratings, they will give you a voltage like 250 volts. That's the maximum voltage difference you can put on it before it will start arcing. Once it starts arcing, you start drilling holes through the dielectric and you ruin it. So you don't want to exceed the maximum voltage because you basically ruin your capacitor. So then we have paraffined paper, paper that's been soaked in wax. That soaked in wax paper has a dielectric strength about twice that of air, which means that you would make for the same physical dimensions twice the capacitance. And the dielectric strength is 40 to 60 kilovolts per millimeter, so it can hold also a much higher voltage. And then you go through and look at the other materials and you see what's the best dielectric to use? Mica. What two reasons make mica the best material to use as your dielectric? It has both the highest dielectric constant, which means for the same physical dimensions, you'll have the highest capacitance, and it has the highest dielectric strength, meaning you'll be able to have the highest voltage for the same physical dimensions. So it gives you the best both for how much voltage you can put on it and for the capacitance. So when you get things like the, going back a page, 3 pages, things like this, what they've done is they've taken sheets of foil and sheets of mica and wrapped them up tightly to get the capacitor. That's why it's in a cylindrical form, because they just wrap them up tightly. Okay, now for the energy stored. We can make a graph. Yeah, I took out the graph. We can make a graph of the energy required, the work to move charge across, and the charge that's been moved across. And we would see something that looks like that. That is what I described earlier about when you move charge across, the voltage goes up. Because the voltage went up, I should have put V here, not W. Because the voltage went up, it's going to take more work to move the next charge across, and the voltage is proportional to the charge separation. And so when you get to a charge, the amount of work that was required is the area under this. Work is force times distance, right? Or as we have here, Q dV, we worked that out before. What does the D mean? I'm just going to rewrite this. The change in potential energy to move a charge across is the charge you move, Q, times the voltage difference, delta V, that you move it through. In calculus, you do the integral, but even without calculus, you can say the area under the line is going to be the energy stored. And so that's a triangle, 1/2 the charge is CV, so that's where we get the CV from, and then the V. So the energy stored by a capacitor is 1/2 the capacitance multiplied by the voltage stored on it squared. Now I can take this and I can rewrite it in different parameters because we know that C is equal to Q over V. This is equal to 1/2 Q over V times V squared, or 1/2 QV. Or I could also solve it one more way using that and eliminating V instead of eliminating C. I'm not going to. What's the purpose of the capacitor once again? Store energy in the form of charge separation, or alternatively in the form of electric field. Okay, so we've worked through very quickly, I know hand waving mostly, how we get the energy stored, 1/2 CV squared or 1/2 QV, or 1/2, V squared over, Q squared over C, I think. We've worked through that, and we know the physical relationship for capacitance based on its dimensions. Let me ask you a quick question. Let me ask you, what if I took a capacitor, so here's a capacitor, And then I took another capacitor and I connected the capacitors together like this. Would that be a bigger or a smaller capacitor? Okay, bigger. Everybody said bigger. Why? Because there's more surface area. Good. You could view this the same as if I had, instead of connecting them, whoa, I was supposed to delete. No, let's try it that way. Instead of connecting them there, I could have just connected them here, right? And then you say, oh yes, the area is definitely bigger, so it's going to be a bigger capacitance. So this is adding capacitors in parallel. We call this parallel when we connect the ends together. And so in parallel, C increases. What if instead of parallel, we did them in what we call series? Is that going to make it a bigger or a smaller capacitance? It's smaller. Did you guys all know that just from preparing for class? Okay, well good, then that's really working. Let's go through the derivation of Y. Insert a white page. Where's my page? Okay. Do it again. Page manipulation, insert, white page, check mark. There it is. Okay. So let's start by saying I have a capacitor. Oh, excellent. Life is good. At least by now I've learned how to make it come back and work. I have a capacitor and I'm going to connect it to a battery. This here is the symbol for a battery. I need to explain the symbol a little bit. This here is the symbol for a cell. A cell is a voltaic cell. It's something that uses a chemical reaction to produce a energy for the charge. Basically, you take a lead acid battery. You have two posts in there, and one is lead, and I think the other is zinc. And then you have sulfuric acid. And the sulfuric acid causes reactions on each of the posts that will take ions from one post to the other. And so what happens is you move charge because of the chemical reaction in there. And so that's what makes you have a certain voltage. And typically a cell will have somewhere in the ballpark of 1 volt per cell. Now, if you have something like a AAA battery, it's not a battery at all. It's a single cell. It's a AAA cell. We just have gotten to the point in America where nobody knows what a cell means and they call it a battery. So if it's AAA, it's really a cell, and the voltage marked on there might be between 1.2 to 1.4, depends on what type of chemical reaction is going on, but that's the voltage for one cell. But what if you wanted a 9 volt instead of a 1.4 volt? Then you have to put multiple cells together. And so you take a cell and you put another cell. And now, if I start here, I'd go up, say 1.4, up another 1.4, and I have 2.8 volts. And when we put more than one together, we call it a battery. It's a battery of cells. And so the symbol for battery is just taking out this separator and showing, sometimes they show 2 cells, sometimes they show 3 cells. But these are batteries here. Now, with the symbol for a cell, the long line is always the positive side. So you don't have to mark it, it's given. The long line is positive, the short line is negative. The symbol for the capacitor is made to look like a parallel plate capacitor. What would you say about the lengths of the lines for the top and bottom of the capacitor? They're the same. They're equal. Now, there is one further variation on the capacitor. This here. That is also a capacitor. The difference in the two are the one with the curved line is biased. It only works correctly if you put positive on the side that's straight and negative on the other side. If it has parallel lines, it works the same regardless of which direction you put it. And it has to do, if you put a dielectric that doesn't easily rotate, then you have this version here. If you put a dielectric that easily rotates or no dielectric, then you have this version. Okay, so symbols explained. If I connect this battery to my capacitor, what is going to happen?
It's going to charge it.
It's going to charge it. So I'm going to have electrons that flow away. Now I'm going to change my wording. I've talked about electron motion so far. In physics, we talk about current. Current is the rate at which charge flows. Delta Q over delta T. Inherent to that is that you're talking about positive charge. But what is moving through my wires? Electrons, which have a negative charge. So the direction that electrons flow is going to be the opposite direction for positive charge flow. And there's no actual positive charge flow. So we talk about the mythical positive charge flow, but it's perfectly accurate still to talk about the current because a negative charge flowing left is exactly the same as a positive charge flowing right. And so we draw this as a current flowing out of the positive to one side of the capacitor. The symbol we use for current is I. The unit for current, what's the unit of charge? Coulombs. And for time? So the unit is coulombs per second, which we call an ampere. So we have the current that flows from the positive to one side of the capacitor plate. What's that going to do to the capacitor plate that the charge flows to, that the current flows to? It's going to make it which one, positive or negative? So that's going to have plus Q on it. Now, we can look at this two ways, but let's just stay on the capacitor. If the top plate is now positive, what's it going to do to the bottom plate? It's going to attract electrons. So it's going to attract electrons or repel mythical charge, positive charge. So we're going to have a current that goes like that, making this side have a negative charge. And because the battery does not create or store charge, the amount of charge that leaves the bottom plate has to be the same as the amount of charge that arrives at the top plate, so the two charges are equal. So that's what happens if I put one capacitor in. Of course, how long does the current flow? Only until the capacitor is charged up, right? Then it stops and you reach equilibrium. So now I'm just going to look at equilibrium, not draw any arrows. Let's say I take a battery now and I connect it to three capacitors all connected up. So I have my voltage here. I have C1, C2, C3. What am I going to have on the top of C1? I'm going to have a positive charge. So I'm going to have plus Q1 here. And where's that charge? All the electrons that left that top, where are they going to end up? The bottom. So I'm going to have a minus Q1 down here. It has to be the same because my battery can't store or create charge or destroy charge. It just moves it. Well, if I have plus Q on the top, what am I going to have on the plate below it? Minus Q. And that minus Q, of course, is electrons that came from this one, so it has to have plus Q. What's the key here? In series, we call it in series when they're one right after the other. So you have no alternative for a pathway but going one to the next. So in series, all the capacitors have the same charge. So I can take this and I can say, okay, since Q is equal to VC, then V1 must equal Q1 over C1, right? And V2 is likewise equal to Q2 over C2. V3 is equal to Q3 over C3. But what do we say about those Qs? They're all the same. So I'm just going to drop off the numbers since they're all the same. My voltage is my energy per charge. This next thing I'm going to teach you is called Kirchhoff's voltage law, and it's, or not voltage, yes it is, Kirchhoff's voltage law. And it's very, very simple. We learned in thermodynamics that energy can't be created or destroyed, right? So if I start here and I go from here to here, because of that battery, the potential energy per charge has gone up by V, right? Now if I go from here to here, it's going to drop by V1. And if I go from here to here, it'll drop by V2. And finally, from there to here, it drops by V3. And then I'm back to my starting point. Well, when I get back to my starting point, what should my energy be? What it started with. It's just like if I hike up to the top of a mountain and then I come down by another trail, if I get to my starting point, I'm at the same elevation. I'm at the same, remember, elevation is the same as voltage. Elevation for gravitational potential energy, voltage for electric potential energy. So it's the same idea. I have to be at the same voltage. So that means I have to have that the V of the battery is equal to V1 plus V2 plus V3. Now substituting, since Q is V over C, the voltage total can be written as Q divided by C total. C total for when they're in series. So I'm actually going to write CS for C series. But that's equal to, substituting from what we have, Q over C1 plus Q over C2 plus Q over C3. Now, we're all really smart people. I believe every one of you is smart, just in case you've ever wondered. I believe everyone here can see something that we can cancel from every term, right? So let's go ahead and cancel the C's. Yeah, I think I'm funny too. I'm sorry. We'll cancel the Q's, and that leaves us 1 over C series is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So that's how you actually can get the total capacitance if you put them in series. Now that's not a very drawn out derivation, but I kind of find it fun because, I don't know, it just seems like it's a little tricky. So if you look at this, if each capacitor was, let's say, 10, 1 over 10 plus 1 over 10 plus 1 over 10 is, of course, 3 over 10. And so if 3 over 10 is 1 over C3, you invert that 10 over 3, and that gives you 3 1/3. Is 3 1/3 bigger or smaller than 10? Smaller, yeah. So when you put capacitors in series, you always end up with a smaller equivalent capacitance. And the reason is because each capacitor is going to have the same charge. Has to have the same charge because the charge is trapped between the plate of one capacitor and the plate of the next. What leaves one has to go to the next. They all have to have the same charge. So that's the reason that they have the same charge, and that's what leads us to decreasing capacitance when you put capacitors in series. We generally don't want to lower the capacitance. We want to increase it, right? We can always make a capacitance that's smaller just, by dimensions. So that brings us to the second one. What if my circuit is like this? Now what's going to be the same for each of my capacitors? They have the same what? They have the same voltage because the top of each capacitor is connected to one side of the battery. The bottom of each capacitor is connected to the other. That's what we call parallel. So they all have the same voltage. What's different? The charge. And so I'm going to say Q1 is equal to C1V, Q2 is equal to C2V, Q3 is equal to C3V, and the total charge that leaves the battery is distributed among the three capacitors, so I'm going to have Q is equal to Q1 plus Q2 plus Q3, which gives me Q equals VC, oh my goodness, I put S for parallel. This whole thing was, oh wait, no, that was series. This is parallel, I'm good. Except for right now, the brain fart. VC parallel is equal to C1V plus C2V plus C3V. And what can I cancel from each one? V. And so if I cancel all the V's, oh man, I'm having a good day. Then I'm left with C parallel is equal to C1 plus C2 plus C3. So if you add the capacitors in parallel, it's always going to be a bigger capacitance. If you add them in series, it's always going to be a smaller capacitance. Why is it bigger in parallel? Because they all have the same voltage. Okay. Keyboards. We all use them. This is one way of making a keyboard switch. You press on the key and you want your computer to know you pressed on the key. And so one way of doing it is you have the key just goes down to a plate and down below is another plate. And you have a small voltage, like 5 volts, between those two plates. So you have a fixed voltage. When you press the key, what happens to the capacitor? Let's go with very broad terms. Physical dimensions. What happens to the physical dimensions of the capacitor when you depress the key? The separation gets smaller. When the separation gets smaller, that affects the capacitance. What happens to the capacitance when the separation gets smaller? The capacitance goes up. But if the capacitance goes up and you keep a fixed voltage, what happens to the charge? If the capacitance goes up, since Q is equal to VC, the charge has to go up. So when you press that key, the charge has to go up, which means you have to have a current flow for the charge to go up. And so what you detect, what your computer's doing to detect this keyboard, is when there is a current going to that key, it says it was depressed. And then when you let up, charge has to leave, there's a current in the other direction, it says off. Now it was released. And so it actually is measuring when you press down and when you let up. So that's one way of making a switch. Something I really like at home is the lamps next to my bed. I just touch them and it turns it on. That works in a similar fashion. I touch it, a little bit of current flows through me, it detects that current and flips the switch. Okay, I'm out of time, so let's end with this question and we'll go home and we'll talk about resistors in lab tomorrow. Yeah, channel 33. Waiting for just 2. I really want to wait for the last person because this is the only question, so you get 0 for participation. Can't get it to work. Okay. So we had 2, 18, and 0. Eee. That was not right. The charge does not remain constant. The voltage remains constant, but because the capacitance goes up, then you're going to have the charge goes up. So the correct answer was charge increases. If you answered A and you're unsure, come talk to me so we can make sure we're clear on that. Okay, have a good day.